Hello. So I want to talk to you briefly about two of the most important functions that you might not know about, the hyperbolic sine and the hyperbolic cosine. They're a lot like the regular sine and cosine, but in some ways simpler. Okay, so first, the hyperbolic sine, and I say sinh. Write it S-I-N-H for hyperbolic sine. Sinh of x is defined to be e to the x plus e to the negative x over 2. And the hyperbolic cosine, or cosh of x, like coshing somebody overhead, cosh of x is e to the x plus e to the minus x over 2. And if I plug in x equals 0 for that, since e to the 0 is 1, I get 1 minus 1 over 2, or 0. Sinh of 0 is 0. And for cosh of 0, I get 1 plus 1 over 2, I get 1. Okay, so a lot like sine and cosine, right? So now think about the derivatives. The derivative of sinh of x is e to the x minus e to the minus x times negative 1 from the chain rule. I get cosh. And the derivative of cosh is e to the x plus e to the minus x times negative 1 from the chain rule. So the derivative of cosh is sinh. You notice there's no minus signs, right? Cool. So there is one place you have to kind of pay for the simplicity of the derivatives is, unlike trig functions, hyperbolic cosine squared of x minus hyperbolic sine squared of x equals 1 for all x. This sinh is about the derivative. To actually show this, if I square that and I square that, you can do that, you get the cross terms, etc. This is a little bit of a slog. Okay, so like I say, they're a lot like regular sine and cosine. Let me just show you how they differ. Well, sine of 0 is 0, cos of 0 is 1. They're the same like that. The derivative of sine itself is cosine. That's the same, but the derivative of cosine is negative sine. And then, of course, cos squared plus sine squared of x is 1. All right. So hyperbolic sine and cosine, they're pretty cool. I want to show you the few pictures of them too. I've drawn the pictures, but let's share the screen. And here we go. All right. So let me get rid of this. So here we have hyperbolic sine of x. It grows really quickly. Here we've got hyperbolic cosine of x. And this is the same shape that you get if you have a hanging string or a hanging chain under its own weight. I've drawn pictures here because it's really important in this day of artificial intelligence, the hyperbolic tangent of x. Hyperbolic tangent of x is hyperbolic sine of x divided by hyperbolic cosine of x. And it moves from a horizontal asymptote of -1 as x goes to negative infinity to +1 as x goes to infinity. So it's a nice, smooth function that steps from one value to another. The derivative of a hyperbolic tangent is 1 over hyperbolic cosine squared, very similar to the derivative of regular tangent is 1 over regular cosine squared. Here I got a picture of that. So this is also very useful as a nice sort of hump function. Okay. All right. Let's also go back to here. Look at these. The derivative of cosine, you see, is sine. Of cosh is sinh, right? The derivative starts at 0 and increases. The derivative of this is red curve is negative. Here, the derivative of sinh is always cosh. Sinh is always increasing. So the derivative is always positive. Derivative of sin at 0 is 1, etc. Okay, cool. If I sum those two together, by the way, I get y equals e to the x. That's also something about that. The sum of, from the definitions, you see that the sum of the hyperbolic cosine plus a hyperbolic sine is just the exponential. Let's stop the screen. You see that it's built in here. If I add that and that, these terms cancel, and I get e to the x over 2 plus e to the x over 2. I just get e to the x if I sum them. All right. I'll see you later. Bye.